Alright, so today we're going to be doing a little bit with building some utilities for working with grammars in the context of programming languages or other things. This is something that is based off of an exploration I did, and the best videos that I could find on YouTube with regard to grammars, Ladder, grammar, parsing. It was Ernie Monkey was the name of the YouTube channel. Of course, my local accession. Nope. X profile. My mouse wheel is backwards, so now we can. Okay. Nope. Almost. There we go. This is the course that I went through, and the explanation is adequate, but I thought that I could maybe give a slightly better explanation of how to build a grammar library, or to understand how LR parsers work by building a grammar library for everyone. So let's say grammar utils. Let's call it a lib grammar. So we will start with a grammar in the formal sense. I don't know if I know the definition entirely off the top of my head, but it's something like this. You've got definition by example is a good place to start. You have something where you have a set of symbols, and symbols are broken down roughly into two categories. So you have symbols. Symbol can either be a terminal, and terminals are effectively the same thing as tokens in whatever language we're trying to parse. So this might be things like keywords are tokens, identifiers are tokens, numeric literals are tokens, curly braces, brackets, those sorts of things are all going to be tokens. And then we have non-terminals. And a non-terminal is called such because non-terminals expand into either tokens or into other non-terminals or combinations of tokens and non-terminals, and these usually correspond to entities in your program that have a higher order nature to them. So for example, the whole program might be a non-terminal. A function decal might be a non-terminal. You might also have an expression as a big class of non-terminal. There's lots and lots of these. So these are together, we are going to call terminals and non-terminals taken together as symbols. We are going to create a grammar over these. And a grammar, generally speaking, is going to look something like this. So it's going to have a grammar for some programming language. It might look like this, where a program might be some set of declarations, and maybe that's it. And what is a decals? A decals is either going to be a single declaration, or it's going to be decals followed by it's going to be a single declaration followed by more decals, or it's going to be empty. And we use the lowercase epsilon to designate empty. That means, so this general syntax is that when you see this non-terminal on the right-hand side, it's going to expand into whatever sequence of things on the left-hand side. This is going to expand into the sequence of things on the right-hand side. So decals will expand to either, this is what the vertical bar means, is an or. Decals is either a single declaration, or it's going to be a single declaration followed. I guess I actually wrote this kind of dumb. This is the cost of not having examples written out beforehand. these up. So a declaration is either a single declaration followed by 0 or more, or followed by more declarations, or it can be empty. And then what does a decal look like? It's going to be something like some keyword, maybe func for function, and then maybe it'll be followed by an identifier, and then followed by a open parentheses, followed by a close parentheses, and so on. And there's dot dot dot. Well, this is we'll go through. So an actual programming language grammar is going to be a bit more complicated than what we want to start with. We're going to build the foundation for working with simple sort of dummy grammars, and then once we have that, we can see how we can build up a programming language from there. So let's start with something like this. We can have A, which will turn into B, followed by A. We can have B, which will turn into B, followed by 8. And then B can also turn into BB. This is just something contrived I came up with off the top of my head. And if this is our start symbol, we may imagine that this will parse BBA. It will parse what would it be? BBA. Yeah, this is tedious. We'll go to actually coding this up, and then the actual examples that we will work with will come through a little bit better. So what is a grammar? And I have a sort of reference, some junk code I have on the other monitor that we're going to be kind of working from as an example. So a grammar is going to be a list of symbols and it's going to be a list of rules. And so what is a symbol in this context? So for what we want to do, a symbol, we'll just say that it has a name. And well, let's do this slightly differently than the example that I have off here. So there's going to be an enum. Either it can be a terminal. In that case, well, let's do it the way that I have it written here, and then we'll go ahead and adapt it the way that I was planning to anyway. So we're going to have a symbol. And then what does a rule look like? Well, a rule is going to have a left-hand side, and the left-hand side is going to be a symbol, and the right-hand side is going to be a vector of symbols. However, we want to have it so that these are effectively references to other, these symbols here need to be pointing back into the grammar data structure, and so we actually want to come up with a little new type struct, just wrapping it. We'll call it symbol IDX, and we'll say usize. And so what that is going to mean is that instead of storing the symbols or symbol data directly here, we're going to do symbol IDX there, symbol IDX there. And so our rule data is simply the data of whatever number, if we have our list of symbols here. So we might have symbol number 0 will be A, symbol number, usually I like to put the non-terminals first, so let's put symbol number 0 is little a, symbol, and symbol 1 is going to be little b, symbol number 2 is going to be capital A, symbol number 3 is going to be capital B. And so that accounts for everything that we see here. The first rule then would be expressed as the left-hand side is going to be 2. and the right hand side is going to be the vector. It'd be 3, 0. And so this is the representation that we're going to be giving to the rule data up above. Why is this red? My IDE is still broken here. This should work. Rule data. Let's go ahead. Okay, there's no actual issues here. My LSP is just kind of dying. So we have rule data, we have symbol data, and where do we want to go from there? So the first thing that I decided to do when I was writing this up the first time, I'm actually going to make these private structs, was to create these helper structs, symbol, tick G for grammar, and what a symbol is actually the sort of user handle for operating with symbol data through a grammar. So we will do symbol IDX there. Oops. So we're going to use the lifetime tick G to represent the grammar going forward on this. And this will make our life a lot easier because we can now have simple tick G symbol. We can we'll worry about that when we come to it. So what are we actually trying to do with this data structure is let's write some tests that we're going to be playing with. So test. And then there's one other thing that I found kind of useful to work with is grammar builder. Is going to be a structure that allows us to build these grammars in a declarative way. So we're going to put symbols. I guess these are the same as this. And then we're going to do impl grammar builder pub fun new, and that is going to give us a grammar builder. Actually, that's going to be pretty easy to put together. Nope. Why is my LSP totally broken? Symbols rules is going to be empty. And actually, we're going to call this grammar to make the LSP look nice. So that's going to give us the ability to create a builder, and then the grammar builder itself is going to look more like this. Pub fun symbol, and it's going to take a mutable self and a name for a symbol. And it's going to take anything that is sufficiently stringy, and it's going to just modify itself and return itself. And that's going to be symbols, symbols.push name.into. So that allows us to push the symbol onto the list of symbols and then return self. And then we're going to do something similar for pushing a rule. So for the rule, we're going to have the LHS is going to take it's going to take the left-hand side, and then it's also going to take the right-hand side as a slice of S's. I'm going to say as ref stir on these things. I think that should be a little bit nicer. What is this here? Try wrapping the expression. Symbol data. Oh, that's right. So symbol data, make that into the name. And then, so for pushing a rule, we actually need to look up all the symbol indices. So given a name, which we can just assume is that, we can say symbol index like that, or symbol IDX is what I called it. And this is going to be just a matter of for symbol data in self dot, I'll just say symbol and symbols. If symbol dot name equals symbol name, we're going to return. We need the index. We need to. We need the index. So we're going to actually enumerate over that. And we're going to return symbol IDX in that case, and then over here we're just going to panic no such symbol and give the name, which is symbol name. And then up here what we're going to do is we're going to add to the rules, and when we add to the rules we're going to do rule data. So we need the LHS, which the LHS is going to be the parameter LHS, but we need to do self.symbol index for LHS.sref. There we go. And then the right-hand side, we need to convert this RHS. Let RHS equals RHS.iter.map. And we're going to take each of those symbol names and we're going to do self.symbol index of symbol name dot collect. And we're going to store that. Just use the inference there. We're going to store that as a vec of symbol IDXs. We need to do as ref there. And over here we just say that is the right hand side. This should be rules. And this should also be rules. Grammar builder. There we go. Method symbol. Symbol index. So we can go ahead, just make sure my LSP is telling me everything looks like it checks out. And so we're going to build up a grammar, like in our example here, A to B to A. So we're going to do grammar new, let grammar equals, and we're going to do on that dot symbol, little a, little b, capital A, capital B. And then finally we need one more method here, which is going to be pub fun build, and that's going to just consume self and return instead a grammar, which is going to be just self dot symbols, self dot rules for symbols and for rules. And so we need to do dot build there, and there is our grammar. We will then print this out just to make sure that everything looks good. This is going to joke on the fact that the symbol data doesn't have a debug. We're actually going to implement a custom debug for symbol data. It'll make our lives so much easier. rule data, we're going to do something similar. We're going to implement debug. And what we're going to do here is self.lhs. This needs to derive debug, and then an arrow, and then the right-hand side is going to be a little bit self.rhs.iter.map symbol. We want to do format symbol. Does that work? No, we want to do .collect. Turn that into a vector, and then .join on a space. Symbol IDX does not implement debug. That's right. We need to convert. Okay, yeah. So this is where having these helper types is going to be useful. So we are going to just move all this debug stuff together. We are going to have two public structs that are going to help us out with this. This one is called symbol. It's actually going to take the lifetime G, and we're going to have grammar, tick G, grammar, and then index. Did I write this already? Oh, I did. I wrote exactly this. So we're just going to go ahead and do something. The other part that we need, which is to have the rule data index. Do we have a rule index? We don't have a rule index. We need rule index. Okay, so this is going to be similar. So it's going to be a rule index and a grammar. And now what we're going to do is we don't want debug for symbol data. We want debug for an actual symbol. Okay, so this is where impl tick G for symbol of tick G. So given a symbol, we want to be able to get the data. Down here, we're going to do something similar with rule. We're going to get the rule data for this. So we're going to go into rules. And okay, so now we can implement debug for the symbol, which has not only the data, but also it is aware of what grammar it comes from. So I can, down here, I can do something nice. I can say name of a symbol, and this is going to be a string. We're just going to go ahead and copy it, and the name is going to be self.data.name.clone. And then down on the, not the grammar, but the rule, we're going to have pub fun. The left-hand side is going to be a symbol of tick G, and that's going to be self.lhs is the index. So we're going to do a symbol where the grammar is self.grammar, and the index is going to be the left-hand side index. I need to get the data. Move occurs because symbol index does not have copy trait. Derive clone copy EQ partial EQ for both of those indices types, and we don't want to implement debug on that. I'm going to get rid of this. So we can do self.name on that. So that allows us to print out a symbol, and then for the rule data, we're going to do something similar. We need the left-hand side. We have that. We need the right-hand side. It's going to be similar, except it's going to give us a vec of symbols. So for symbol in self.data.rhs, I believe that gives us a symbol index. Okay. We need a result. It's going to be a vector. We're going to start pushing, and then a result. And then what we need to do is push into that vector result.push symbol. And what is that going to be? It's going to be symbol, I guess. Just do that. And so now, okay. So we have our right-hand side, our left-hand side for the rules. That makes it a lot easier to do this then. So for a rule, not rule data, but for a rule, that gives me the ability to query the right-hand side. That creates a clone, so we can do into iter, and then we're going to, then we get an actual symbol then, as opposed to a symbol index, and it allows us to format things. Over here, just do let LHS equal self dot LHS format. Then we have LHS and RHS, a single right, and everything looks good. So what do we do here? We want to debug grammar. Grammar doesn't implement the debug trait, we still didn't do that. So we need to go back up here, and this doesn't take a G. Grammar, I'm gonna auto implement that. We're gonna do for rule in self.rules. And we are simply going to write a len for each of the rules. Rule data does not implement the debug trait. We need to call that, remove the arguments. Okay, we can fix this. We need to go down here. We do impl grammar. Pub fun. Do I have impl grammar? Impl grammar. I do. Let's keep these together then. And the rules are going to give us a vector of rule tick, vector of rules, which is going to be the same lifetime as the self parameter. For rule in self.rules. Result.push rule, and it needs a grammar, which is self, and it needs an index. So we actually only need to iterate over however many there are. Index rule, I guess rule IDX index, that works. Okay, so now when we want to print out the grammar, we can do that. I think we're all good there. So we can do cargo test, print it out. we need both the dash dash and the dash dash no capture, and that will tell us that the grammar is it doesn't look right. That looks very wrong. For rule and rules, where did our rule and rules go? Did we not copy something over? Symbol A. We could do debug, drive, debug on our grammar builder and print the, no, that's not going to work so easily. Well, we can do it the obnoxious way, and then we can, once we find the problem, then we can go and fix it. So it's probably just easier to make a copy here. Debug grammar. Okay, so it looks like the symbols are being added. Oh, I didn't add any rules. No wonder it didn't work. Oops. So what do we need to do? We need to do rule A, and we'll do capital B, A. Does that look good? And then B, little b, and capital A, and B to BB. And now we should be getting, okay, so there's the first rule here is A to BA. This one is B to BA. This one is B to BB. Okay, and then just if we wanted to change this a little bit, if we had an empty one, there's no epsilon here. I'm not going to do like some obnoxious Unicode thing where I had an epsilon, so we're just going to leave that there. Okay, so this is our basic data structure of the grammar. So any grammar can be expressed in this way, any context-free grammar. Very often there's other ornamentation that you can have, such as you'll often see cases where in an actual grammar, for let's say a programming language, you might have something like decal, or you'll see like program is a, and there's different syntax. It could be decal star, 0 or more decals, or it might sometimes be in curly braces, meaning 0 or more decals. And this can always be expanded into something like decals, and then this decals over here becomes either a decal followed by decals, oh, is that my phone in the other room? Of course it is. Or an epsilon. I will be right back. Even the syntax here is really an abbreviation for just rewriting decals out twice in here and having just an additional production with the same non-terminal on the other side. And so this is going to be syntactic sugar that we will address in sort of a future version of working with this. So some of the things that we are going to need to do in order to start writing an LR parser or any other kind of parser is calculating some metadata derived from this grammar. And that would be, at least in the implementation that I have, there's 3 basic pieces of metadata. You need to know which symbols, which non-terminals in particular, These are all for non-terminals. You need to know which non-terminals are nullable. You need to know the first sets, and you need to know the follow sets of each non-terminal. And these three things will give you the ability to build out the parse tables as you need them for when you want to start trying to build some kind of LR, LALR, GLR parsers. So I think I'm going to stop the video here, and we will do those next time.